Hello, good afternoon everyone. My name is Abhay Kumar. I am from Department of Artificial Intelligence and Data Science. Today we will be going to see different sorting algorithms. What is insertion sort, right? So suppose for example, if you want to insert any record onto your documents, or if you want to add any information onto your database, what do? You just go, you put up some edit option and then you put it into the insert mode, right? Or if you want to add something into the document, you just open up the document and insert the document. But in data structures, there is a different ideology here. What is the different ideology? Insertion sort is a simple algorithm that builds on the final sorted array one item at a time. The same thing again. Okay, but how does it do? Final sorted array. Okay, it works on the final sorted array. Okay, and what is it? It is a comparison based sorting algorithm. And how does it work? Dividing the input array into a sorted array and an unsorted region. So you have few elements, 1, 2, 3, 4 something. So whichever element you are taking, that is known to be a region. Okay, so you have an known region and you have an sorted region. Sorry, unsorted region, right? So unsorted region is where you don't have any information, or you might be knowing the elements, but you are still you are not working on it. Okay, so that is known as your unsorted region, right? So now what happens is that, okay, now we understood what is sorted, and then we say that we have something called unsorted region, right? So now initially the sorted region contains the first element of the array and the unsorted region contains the rest of the elements, which I have just explained you. Okay, and then the algorithm repeatedly takes an element from the unsorted region and inserts it into the correct position within the sorted region. Very important, guys. Okay, so this is what we have to consider. Okay, so what do? You have taken an element. Okay, after taking that element, what are you going to do? You have taken the unsorted element region also, and then you are putting up that particular element into the correct position, and then getting the merge into the sorted array, right? So we'll just see an example very shortly. Okay, before getting into the example, I would like to describe some algorithm. Okay, or again the steps, how do we perform this insertion sort. Okay, the first step is that if the element is the first element, assume that it's already sorted, return 1. Okay, which means true. Okay, then pick the next element and store it separately in a key. Okay, as I just told you, we store it. So one element is known, second element we are taking it as a key. Right, now compare the key with all the elements in sorted array. Okay, now there is only one key. So what you do, you try to see that if there is any match or not. Okay, then if the element in the sorted array is smaller than the current element, then move to the next element, else shift greater elements in the array towards the right. Okay, so we'll see that in an example. Okay, this is just an basic step by step process. How do you do your insertion sort, right? So you move on. Okay, then after that insert the value. Okay, repeat until the array is sorted. So this is a 6-step process. Okay, this is a 6-step process where you tell that we can perform this insertion sort. Okay, so now let us see this example. Okay, everyone, so you have elements called 4, 3, 2, 10, 12, 1, 5 and 6. Okay, so we have almost 8 elements. Okay, where we see that initial level the sorted region has 2 elements, 4 and 3, right? So what were you doing? We start sorting using regions. Okay, so let's consider 2 to be one region, this next 2 elements to be one region, next 2 elements to be one region, right? So if you divide those in regions, so the first element here, okay, so the first element here in sense 4 and 3, let's consider, so we compare. Okay, so comparison based, what comes? 4 and 3. Okay, so here 3 and 4 will come, and other elements are left like that only. Okay, now next, okay, one region is sorted, now second region, okay, 2, 10, which is already sorted, so we need not to worry about, right? So now what we do, this still here, okay, we are all fine. Okay, done. But now when we are focusing on the fourth stage, okay, or fourth iteration, you see now what did we do? We are taking up 10 and 12 to be consideration, and which also 12 is also an element and is already sorted, right? So we tell that till here it's all fine. Okay, so all the items are sorted and they are in their own region, respective region. Okay, and now what we do is that we see the other unexplored area which is known to be unsorted region. Okay, so unsorted region. So what do we see? We see that we have we are left with 1, 5 and 6. Okay, so now how do we start comparing? We start comparing that 2, 3, 4, 10, 12 is already announced. Okay, 1 is now the element which we need to focus on. So we tell that so we use 1 as an element and we see that okay, this is lower than the initial element. So what we do? We directly pull it into this particular block, okay, or the region and put it there. Okay, sorted region. Okay, so guys, you see here all the green are the sorted regions, all the red are non-sorted regions. Okay, for your better understanding, right? So we do that. Okay, then what happens? 1, 2, 3, 4, 10, 12. Okay, next is the fifth element. So in the fifth element, what are we doing? In the fifth element, we see that, yeah, in the fifth element, you see that, the comparison. Okay, and based on the comparison, we tell that no, this is very, lowest than the, 5 is less than 12. Yes, it is less than 12. So what we are doing? We are sorting it out. Okay, then after that what we are doing? We are putting 10 and 12 into the consideration. Okay, and then we have a last element which is 6, and we also compare with all the elements, and then we put up our final array which is 1, 2, 3, 4, 5, 6, 10 and 12. Okay, so this is how we use insertion sort for the execution. Okay, great. So I hope you are now clear with the merge sort and the insertion sort, right? So this is small, Python based program code, okay, where insertion sort is your Python library which is majorly used, and your array is being considered to be a parameter. Okay, and we use for loop and some while loop condition where we see that what elements are put in the sorted region and what other elements are being captured from the current element into the correct position, right? So this is how we write an Python program code for your insertion sort. Okay, so this is a small list. Okay, insertion sort, we are just calling up the function there using our list. Okay, then we tell that what is a sorted array, then my list, and we get our sorted array. Okay, right. So this is what our insertion sort programming code looks like. Okay, clear? Yeah. So moving to the last, no, not the last, but important complexity part of our insertion sort. The worst case time complexity O of n square. Why is that so? In the worst case scenario where the input array is in the reverse order, insertion sort will require the maximum number of comparison and shifts for each element. That's true, right? So we have seen that 5 and 6 are in the last corner of the element. So what do? You just have to compare all the elements and then put into the correct order, right? So that is why we tell that the worst case time complexity is O of n square. This results in quadratic time complexity where n is the number of elements in the array. Very true, right? N is equal to n into 1, 2, 3, 4, 5, 6, so on, right? Then what do you see? Sorry guys, yeah. Then we see that the worst case occurs when the array is in the ascending order. Very true, because it requires the maximum number of comparisons and element movements, right? So this is the O of n square. Okay, so guys, before getting into the detail, right, you have to understand what is big O notation, okay, what is asymptotic notations and all this. Okay, so that I will cover up in some other session, but why is this particular complexity and all these algorithms are into picture is because they are in a sense helpful for your job opportunities or any coding platform based activities or such. Okay, yeah. So see, for every complexity there are 3 different cases, guys. One is best case, worst case, and what is the auxiliary space, or you can say space complexity, right? So you have seen the worst case complexity for your insertion sort, and here in the best case time complexity we have O of n, right? So where this tells that only one element is being considered and only that particular element is being captured, and the action is providing on that. right? So that is why we tell that in the best case scenario, when the input array is already sorted, insertion sort is very efficient. It will require only one comparison for each element, and no element movement will be needed. Okay, this results in a linear time complexity of O of n. So linear time in a sense 2, 4, 6, 8, 10. Okay, so there is no odd sequence there. Fine. Okay. And the average, another part is that average case scenario. So average case scenario is O of n square again, which is also known to be as worst case scenario is equal to average case scenario. Okay, so here in the average case, the number of the comparisons and the elements movements fall between the worst case and best case scenarios. Okay, on average, insertion sort exhibits a quadratic time complexity. Right, so here this is the very important part again, quadratic time complexity. What does this mean again? So this means that you are going into some expression kind of part or complexity. Okay, so we can call this as to be a polynomial or an equation kind of thing. Okay, this was all about your insertion sort with all the time complexities, right? So thank you all for your precious time, and let's see in our next session, and we'll see to explore more algorithms and also their time complexity analysis as well. Okay, thank you all. Have a good day. Bye bye.
Like, share and subscribe. Hit the bell icon for more updates.